before solving it, let's do one thing. Let's do something called non-dimensionalization. So, you have done non-dimensionalization in the last semester's course? No? You heard about non-dimensional numbers, Reynolds number, that is a non-dimensional number, right. So, we are going to see this, okay, the next part in which we will see how to do non-dimensionalization, what is meant by non-dimensionalization, but at this point itself we can actually start doing that, and I think it is worth doing it at this point. So, before solving, let us do something called non-dimensionalization of equations. So, what is meant by non-dimensionalization? You are going to make all the variables non-dimensional. So, for example, what is the dimensions of velocity? It is just length per time. Okay. You want to now make it a non-dimensional quantity. That means you get rid of the units from that. That is what is meant by non-dimensionalization. Okay. So, we will actually non-dimensionalize each term. So, how do we do that? How can we get rid of dimensions of velocity? You have to divide it with another quantity which has the units of velocity. Okay. So, that is one thing. What is the other quantity that we need to non-dimensionalize? Length, r, okay, radius. See, what are we expecting to see? We are expecting to see uz as a function of r. That is our objective. Okay. So, we want to non-dimensionalize our velocity, we want to non-dimensionalize our length. Okay. So, now we have to do that, we need to find out what can we use to non-dimensionalize velocity first, or let us non-dimensionalize length first. What can we use to non-dimensionalize my length? So, what we need to do is to choose something called a characteristic length. Okay, some constant length from the problem. So, can you think about some constant length that we have in the problem right now? Radius. Okay, it could be radius or it could be diameter, depending upon whichever you want to do, we can do that. Let us just choose radius. So, let us choose characteristic length as radius of the pipe. Then what we do? We will define a non-dimensional radius . R star is equal to R divided by capital R. So, this R, small r, was our original radius which had the dimensions of length. We have divided it with the pipe radius, okay, and we have gotten an R star which would now vary from 0 to 1. Okay, that is a good thing about, another good thing about non-dimensionalization. You have gotten rid of the length and you would basically say that things are going to change between 0 and 1. If you had taken diameter, you would have found that it would go between 0 and half. That is all, okay. But it is always going to go in that range. It is not going to go from 0 to 1000 or 10,000 to some 1 lakh. Okay, that does not come out. It is basically going to be a number which is going to be of the order of 1. When I say also order of 1, it is around 1. So, that. So, radius is done. The other one which we need is velocity. So, we need to get something called a characteristic velocity. What can be a characteristic velocity? Pipe? What is the velocity at the radius of the pipe? 0. So, there is no point in taking that because we are going to divide with 0 and we are going to end up with problems everywhere. Maximum velocity is a possibility, but we do not know what it is at the moment. But let us say that, okay, let us just define a velocity, say u, which let it be the maximum velocity. Where does the maximum velocity appear? At the center. Okay. So, we will use u, which we do not know, but let us just take it. So, and therefore, I can define my u z star, the non-dimensional velocity is equal to u divided by capital U. Now, can you substitute this into your differential equation? that differential equation. So, dp by dz, okay, is just a constant that you have applied. So, why dp by dz is a constant, by the way? Nandini Vasuki, why dp by dz is a constant? Do we know dp by dz is a constant? Yeah, but you have applied on one side and then you do not have control over flow. Nikhil? Nikhil. Imagine there are only two terms, one is a function of radius, the other is a function of z. So, if there are two terms which are equal, one is a function of radius, other is a function of z, then the only possibility is each of them are constant. That is the argument we had for the 2D flow. Okay, it is the same thing. So, dp by dz is a constant. So, you need to non-dimensionalize other terms, mu 1 by, so this tells me that r is equal to r star r, this tells me this is uz, right, uz is equal to capital U times uz star. So, let us substitute mu into 1 by r star r del by del of r star r of r star r u z star u is equal to just dp by dz, some constant that we have applied. Clear? So, what do you end up with finally? So, this also is really ordinary derivative, I do not have to maintain partial derivative. 1 by r star d by dr star of r star u z star is equal to, this r and that r can go, there is an extra r there. So, r divided by mu u times dp by dz. That is right. Doubts? Okay. So, you look at this equation now. So, this tells a whole lot of thing. Okay. The right hand side r by mu u dp by dz. So, you have this pipe, you have applied a dp by dz, you have applied it, it has got this radius r, the fluid has a viscosity mu and it has a velocity, maximum velocity u, which must be related to the flow rate. Okay. So, this quantity, so what will be the dimensions of this quantity? What would be the dimensions on the quantity on the left hand side? What is the dimension of r star? Nothing. What is the dimension of uz star? So, what is the dimension on the left hand side? Nothing. So, the dimensions on the right hand side also be nothing. So, the right hand side is actually a non-dimensional number. Okay. It is a non-dimensional number that tells you how the flow is going to be. Okay. It's a, so the entire characteristic of the flow, okay, determined by that non-dimensional number. So, that non-dimensional number is nothing but r by mu u dp by dz. Okay. If you say that number, then the entire flow can be characterized. Okay. In other words, you double r, okay, and then you change you double your u also in some way, then the right hand side does not change, that means the left hand side does not change. The solution that you are going to get will have just this thing as a parameter. So, if you, it is like this. So, you have heard about parametric equations, right? X is equal to r cos theta, y is equal to r sin theta is one of the parametric equation. So, what do we mean by that? Okay. So, it just says that this is a differential equation this is an ordinary differential equation. Okay, there is only one constant in that entire ordinary differential equation, which is this right hand side, which is a unitless constant. It tells you everything about the flow. Originally when we did not know this. So, here if you look at the original equation, okay, that was our original equation. We had a pressure gradient, we had a viscosity, and that is it, and each of them had its own units and so on. Okay. But now we have gotten rid of all that, and we said, oh, look at our entire equation, the entire equation has become non-dimensional, and we have also figured out if we want to change flow in some fashion, this is the quantity that we should look at, okay, nothing else. We do not have to really care about anything else, because we have, so in fact this is going to be related to Reynolds number. We will see that at a later point. Maybe we will see so you get a little more idea about this when we substitute for u, which we will do at a later point. So, this is the non-dimensional version of the equation. So, we can go ahead and solve our original equation, which is that. Can you solve it and tell me what is the solution? You have to do two integrations. What is that? So, you can bring r to the right hand side first. D by dr of r u z is equal to 1 by mu dp by dz r, which if you integrate, it is going to be r u z is equal to 1 by mu dp by dz r square by 2 plus C1, one constant, which I rewrite it as u z is, sorry, there is an d by dr missing, no? I missed somewhere. Oh, I'll be missing from somewhere up. So, your Laplacian del square is 1 by r del by del r of r del by del r of something. So, that would have given me this as del u z by del r. Here I would have a del u z by del r. Here I would have a del u z by del r star. That is okay. So, I missed a del by del here. In the original definition of Laplacian, it is 1 by r del by del r of r del by del r of something. I should have really done that because each of them should be second derivative, and this term I had left it as a first derivative. Okay, then you bring the r again to the right hand side to the second integration, and that is it. Okay, otherwise try from home. So, now we have two constants C1 and C2, and we need to calculate what is C1 and C2, right. Okay. So, what do we need for that? Boundary conditions. What are the boundary conditions? Rahul Humayun. Yeah, what all boundary conditions do we know? You mean along the pipe? You mean here and here? UR is 0 here. I have a fluid that's flowing and coming in. I have a fluid that's going to go out. You mean on the surface of the pipe. So mathematically, how do you write that? So what is that boundary condition called? No, I'm asking what is the word for that boundary condition? What is? So we say at R is equal to capital R, UZ is equal to 0. And I think that's sufficient because we can already throw away one another term from this. So what do we know anything about at R is equal to 0? What is UZ? Yeah. So, but what about this term C1 ln R? At R is equal to 0, what is log 0? V1 must be 0, otherwise it will go to infinity at R is equal to 0, and you can't have infinite velocity. So, that can immediately throw away, and you will have only C2 now left out, okay, and therefore UZ will only be, you can use this boundary condition to determine what is C2. Agreed. Now, this is where the choice of the coordinate system becomes important. Okay. You are able to write R is equal to capital R, UZ is equal to 0. Suppose you had done Cartesian coordinate system, what would you write instead? You would have had written that if x square plus y square is equal to R, then you would have written UZ is equal to 0. Okay. So, the boundary condition become complicated if you actually had solved it in Cartesian coordinate system. Such a thing is much easily written because now you have chosen a cylindrical coordinate system. Okay. So, it is really the shape of the boundary that determines the choice of the coordinate system, because application of boundary condition becomes simpler in that coordinate system. There is no other reason to prefer any coordinate system over anything else. Okay, it is the application of boundary condition, how simple it can be. Clear? Okay. So, substitute that and then tell me what is UZ. 1/2 mu dP by dz R small r square or capital R square? Small r square minus capital R square by 2. Does everybody agree with this expression? So, we have gotten the velocity profile now. Yeah, I think we will continue with the calculation in the next class now. Any doubts? Yeah, I will stop and we will meet tomorrow.